Good morning, everyone. I would like to take a moment today to just go over some of the content we've talked about in the last week, just for the sake of completeness, so that everybody that looks at this video later, if you're studying for exams or whatever, you can see it. The information's all there. So I'll do that. I'm going to go very quickly through the quality presentation and then focus on the quality tools part, the end of this presentation and the beginning of the next one. All of these slides are on Moodle, so you have access to them. You can see them whenever you'd like. You can view them. But I figured it probably made sense just to have kind of a talk through and go through some of these. Um, your exam is on October 5th. I may have mentioned I thought it was next week. It is actually not next week. It is the week after. So we will have class as normal next week, and then the week after I will have off Wednesday. So that you guys can focus on the exam if you'd like. But October 5th will be the day. October 3rd, which is the Monday before the exam, we'll do a class review. And so we'll go over the 4 different chapters we've talked about already. 4 chapters. It'll be what is the supply chain, process management, quality review or quality management, and then quality tools. So we'll have all 4 of those. I will meet with you. For those who are interested, we'll have a quality tools homework problem that I'll go through on video for you. It'll probably be on Wednesday night if you can make it. If not, don't worry about it. I'll have it done and it'll be up there for your viewing whenever you have time. But I wanted to kind of start going through some of the problems in the class since we're going to do a lot of statistics this year. Right. So without further ado, let me just talk about this very quickly. The very beginning, excuse me, very beginning, we talked about quality definitions and different types of quality. We can go a little bit further. If I can hit the screen, yeah. So different dimensions for the quality of goods and services. There's perceived quality, performance. Perceived quality is how the customer sees the quality. And we said that when it comes to service quality, it's really hard to identify because there were 4 I's. And those 4 I's were intangibility, inseparability, inconsistency, and then inventory. So when you're looking at a service quality, it's hard to measure. So people, and even in physical goods, sometimes people can't see the quality in a physical product. And so if people have a perceived quality on something that it's a higher price because the value was much better, the quality is much better, that is a quality dimension that we want to maintain, although albeit an intangible one. Performance, how well does the product perform? Reliability, is it continue to be used over and over again? Does it die? Does it stop? Do the batteries run out? Whatever it is. Aesthetics is what it looks like, how pretty it is. Support is post-purchase support. How well does the company handle that? With support is warranty. So how good is the warranty for the product after I buy it? Is it helpful? Is it not helpful? Durability is how well it can take a beating. So if it falls off the counter, if you drop it accidentally, we probably are all well versed in dropping our phones on the floor and seeing accidentally and then seeing how well they handle.
Don't
So,
lie to me, Brock.
and then features are different features that we have and different bells and whistles for our product. And then finally, conformance is from our supplier side. It's from us as the producer. It's does the product meet the design specs that we had put in place? Design specifications are the data of what a phone or an item should look like, right? So the dimensions of it, how well it performs, the battery life of it. And so we have this that meets the needs of the customer, the design quality. And the conformance quality is, does the product meet its conformance? If great, if so, great. If not, we probably need to scrap it or rework it. All right, so that's the idea we have for these quality goods and services. And again, we said who's responsible for quality? It's everyone, right? Every department, every individual place, every department is responsible for being good quality. It doesn't have to be product quality, right? Logistics could be delivery quality, service quality, getting that out to people. Procurement is quality of the components coming in. Human resources is quality help to people in our company that need benefits or that are interested in taking a leave or whatever it might be. Finance and accounting, clear balance sheets, clear financial statements. Engineering, high quality engineering for the product to be made, good design specifications. Marketing and sales, quality value that we can give to the customer, not lying to the customer, not overselling a product. So quality is important for everybody. And then all of those different components, all those different departments will lead to the final product quality. So even when it comes to the quality of a component, It's not just quality of their services, but in quality of something that's a physical good. Everybody has input into that. So how many products are we making? How fast do we need them? Engineering, what's the quality associated with your engineering design? Logistics, how well can we deliver the product? So everything and everyone's just involved in quality. Here are some of the thought leaders we talked about very briefly. Deming was the first one. He kind of had this idea. As a matter of fact, and I don't know about now, but I know in the 80s and 90s, he was almost seen godlike in Japan because he was the father of this quality management improvement. So everything is important to the customer. There's something called critical to quality, which is what are the absolutely essential needs for the product to meet customer needs. It kind of breaks that a little bit. I think it's Joseph around. Focus, what is the cost of quality analysis? So how do you measure quality and how do you identify that quality has gotten better? We talked about measures last time. And so some of those there. And other individuals, the idea is that quality is free, that we're going to try to focus on 0 defects. Okay, so that's a big thing. So if I make 1,000 different light bulbs, each light bulb works the way that it's supposed to, that there are no defects. Now, that's virtually impossible. But still, it's the goal to strive for, 0 defects. We're going to talk about Six Sigma in a little bit and the amount of defects with Six Sigma. So, and then Kaizen, continuous system improvement, process-oriented view. A company is a value of process thinking or process management, training and development. Then we talked about the cost of quality. So prevention costs, preventing defects, mistake proofing or error proofing, idiot proofing, poka-yoke, so errors aren't made. So we talked about the phone in the shoes as a possibility, so you don't forget your phone because you got to wear your shoes before you leave. Similarly, here's a plug where one lead on the plug is actually wider than the other. So you can't accidentally turn them upside down and potentially reverse the charge or reverse the current on the device, a vacuum, can opener, whatever. And so therefore it can't accidentally break, right? You can only do it one way. Okay. Then we talked about appraisal costs. This is actually looking at inspection and quality levels. You can see the person on the left in the picture actually observing and making sure everything looks right from a first pass as it's being produced. Usually it's done through training and tools, optical equipment, staff. People are just looking to identify where there can be a potential defect in the process. We talked about internal failure costs. It's before delivery to the customer, but the end of the process. Right? So as we're making the product, we get to the end of the process, it's already made, we test it, we try it out and see what happens. Does it fail? Does it work? Again, the 100,000 light bulbs. Every light bulb, if we do a 100% test, works. If we do lot tests, we pick 4 random ones from, say, a lot of 1,000. Can we assume that all 1,000 work? And the reason we do that is to prevent external failure costs. Because when an external failure cost happens, then you have a recall. And the recall is deadly. It's dangerous because it can hurt you financially. The recall costs usually come at the expense of the producer, which means your company is the one paying for it. And the recall costs are so high sometimes that the customer can lose trust in your company. So those are the 4 quality costs of quality: prevention costs, appraisal costs, internal failure costs, and external failure costs. And now I want to go a little bit further into some topic before we get into histograms. There's a reason I talked about histograms last time. And when you're approaching quality improvement, how do you go about doing that? And here, this triangle has 4 different ways of doing it. The first one, the top one, is called plan, do, check, act cycle. This is really simple. This is really easy. So if I have a problem and I come across a problem, how do I improve it? How do I improve the quality of something? So PDCA is the way to do it. And here's how it works. I want to wake up earlier in the morning. Right? I struggle sometimes getting up on Fridays. I don't want to go to class. I don't want to, but I'd like to get up maybe just like maybe 15 minutes earlier. Well, how do you do that? You brainstorm, you plan to do something. I'm going to set my alarm 15 minutes earlier. Then I'm going to do it. I'm going to try it out, set my alarm 15 minutes earlier. I slept in. Didn't really work the way I wanted it to. I check, did I get up earlier? No. And I act on it. And in this case, it didn't work, so I throw it away. So aside from setting my alarm earlier, how would I wake up earlier? Well, maybe I have my clothes laid out the night before, so I don't have to go searching for clothes in the morning. So plan, do, check, act. So I plan to do it. I do it. I check and see if it helped me get up earlier, help me get out earlier, and then I act. Okay, if it's something that worked, then keep it. Otherwise, don't do it. It's really simple, but know that that's a way of doing quality improvement. I'm not sure how to handle this situation. What would I do to try to make things better, to improve the quality, to improve the process, etc.? So plan, do, check, act is a way to do it. So realize what that is. Now on the bottom left, there's something called Six Sigma. So Six Sigma is the approach to quality improvement, and I'll talk about that. PDCA and Six Sigma are very similar, except Six Sigma is very much a more formalized process. It takes days or weeks to go through. It is not a simple, how would I handle this situation, like PDCA is. And so realize that when we talk about the two, they're both methods of improving quality, but Six Sigma is much more formalized, involves many more people. In the middle, it says ISO 9000 series, which is an international quality award. Usually it's ISO 9000, and then it has a colon, and then the year that the company is certified. So like ISO 9000, 2018, right? And ISO 9000, 2006, 2004. And all that means is that you are mindful of quality. You have the process and procedures that the International Standards Organization, or ISO, has put in place, and you are monitoring those. You are making sure that you are quality minded. You're always trying to do PDCA or Six Sigma, that you are trying to meet customer needs and customer quality. You'll see this on buildings or on trucks. They'll say ISO 9000 colon 2018. And that's letting you know that the company is very quality minded. So you'll see that, you'll observe that, and now you'll know what that means. There's also an ISO 14000, which is OSHA, so health and safety. So that when people go into a cold room at a Kroger to get cold goods or frozen goods, they're wearing jackets and gloves so that the employee doesn't get hurt. So, or if you're lifting things, you have a back brace so that just in case that something pulls, it mitigates the employee from getting hurt. So ISO 9000 is quality, ISO 14000 is health and safety. Then the final one is in the bottom right, it's Malcolm Baldrige Award. And what this is, Malcolm Baldrige was a pioneer like Deming on helping and really putting quality first in companies. And you can be recognized in the who's who of quality based on getting this award. So the award is offered once a year. It's usually given to companies that really focus on quality above everything else. And usually there's a financial stipend associated with it. So maybe the last one was 17,000. But yeah, so it's this mindset that if you win the Malcolm Baldrige Award, you are really a quality leader in the industry. So all these things are just what's called TQM, total quality management. These are ways to help companies improve their quality. And so quality terms that you may see when you're going through just everyday life. We talked about Plan, Do, Check, Act, PDCA. It's really just a simple way of improving something. How do I make ramen noodles better? How do I make s'mores better? What would I plan to do? What would be my change? Then I do it, I check to see whether or not it helped improve the quality, and then if it did, take corrective action and you use the changes. If it didn't, get rid of it. So really just a simple way of doing things. Now Six Sigma is the other way. So let me switch slides really quickly here. Come on. Here we go. There we go. All right. Okay. So when we look at quality improvement tools, the different tools that are used to improve quality, the first one we talked about in class last time was histograms. And so to understand Six Sigma, you need to understand how a histogram works. So let me slide through here and show you. This is the histogram. We said it's just measuring a count of different items as they come through a process. So if we look at the dimensions of a phone and then it should be 6 inches tall, we can measure to the 10th of an inch how tall the phone really is. So it's 6 inches, 6.1 inches, 6.2 inches to be simplistic. We could say I think in the example last time we talked about filling an ice cream container, the Ben and Jerry's, 12 ounces for an ice cream container. I'm going to do 2.5 liters as a giant tub of ice cream that you share with your family or friends. Histograms really are just measuring the count of something through. So if we could look to see what the volume is of ice cream as it comes through, we can see how often it hits the average that it should hit. So 2.5 liters. Sometimes it'll hit 2.4 liters. Sometimes it'll hit 2.3 liters. As you can see on the histogram to the right, that's in blue, the ice cream fill, most often it is right on. So 2.5 liters is my average, my mean. And what I find is that my mean is pretty good. So most times the ice cream containers come through, they're at 2.5 liters. They're good. Sometimes they're 2.2, sometimes they're 2.1, sometimes they're 2.7 or 2.9 or 3. But on either side of the graph, it doesn't have it there, but on either side, there's limits. So let's say that our ice cream container, if it's less than 2 liters filled, if it's 2 liters filled, and if it's greater than 3 liters filled, it doesn't make sense. So 3 liters obviously is too much. The ice cream is spilling out over the sides. The lid doesn't fit on correctly. It's a fail. We've got to get rid of it. We just take it, we throw it away, or we rework it. On 2.0 liters, again, it's a fail. People are going to open up the ice cream and say, oh my goodness, where's the ice cream? Who's been eating this? And it's another fail. So we have limits on either side. But on average, you can see that the graph is bell-shaped. So the highest point is the average, and it kind of slopes down where as you go toward the upper and lower limits, it gets smaller and smaller. Now, excuse me, on the right side, on the red graph, the ice cream fill is skewed, which means the average is actually 2.2 liters. It's it's the observation we see most often. And it tends to go, as we get to 2.5, 2.93 liters, it kind of drops off. Fewer and fewer instances of it. So this is a problem. This is not where it needs to be. Our average is 2.5 liters, and really most often we're seeing 2.2 liters. So I could ask you, what's wrong? What should we do with this? Well, you put more ice cream in, right? Make the graph on the red graph on the left look more like the blue graph on the right. And so we call that being skewed. Sorry, I'm losing my voice. So in a histogram, we're always looking for that bell-shaped curve, not just for statistical reasons, but also for just practical reasons. 2.5 liters is what we want. We end up losing money if we end up having too much ice cream. We end up disappointing the customer, potentially losing money if we have too little ice cream. And so we're always playing this game with histograms. Every observation we get, how is it going to look? How is it going to play out? All right, let me switch back to the other slide so we can go a little bit further here. Here we go. All right. So Six Sigma, if you remember from statistics, sigma is a Greek letter, right? And what we're going to do is eliminate defects of variation. So have more consistency every time we see a container of ice cream, a bag of chips, the dimension of my phone, whatever it is, go through. A standard deviation is the square root of the variance. Now, I don't know if you remember that. I'm not going to introduce equations right now, but I just want you to understand the concept. A standard deviation is a square root, or it's a form of variance that we have in our process. So graphically speaking, we have a lower specification and an upper specification for our process, and a mean. So if we go back to our ice cream, 2.5 liters is our mean. Our lower spec is 2 liters. So anything less than 2 liters is a complete fail. We can't possibly sell it. The customer would be upset. Anything greater than 3 liters, which is the upper specification, is too much of a loss of ice cream. It's barely fitting in the container. It looks ugly. It's spilling out over the side. We can't, it's again a fail. We need to get rid of it. So what happens is, in a process, if we measure something like this, we have a bell-shaped curve. Our observations are about right. The mean seems to be the highest point, so it's good. A standard deviation is 66%, I think it's 65%, of the observations in our process. And where are they? So from the mean, if we look at the mean, 66% of our observations are on either side of the mean. And we call that one standard deviation. So if you can imagine On one side, on the left side, as you see, there are these arrows that are there. It has 1 sigma. So this is 2 standard deviations to the lower specification. Or in other words, if I take the first one that's closest to the mean, that is 33% of all of my observations. If I have another one on the other side of the mean, which I don't in this picture, but if I did, that would be another 33% of my observations. So together, less than the mean and greater than the mean are most of my observations, right? So a process that is 2 sigma in this example is how many sigmas I can get from my mean to my lower specification, or how many sigmas I can get from my mean to my upper specification. So this process is a 2 sigma process. In other words, 65%, 66% of my variation is on 1 sigma or either side of the mean. And see the distance of it? It kind of goes halfway between the mean and the lower specification, or halfway between the mean and the upper specification. So that's a 2 sigma process. In other words, 2 standard deviations covers one direction from the mean to one of either the upper or lower specification. The curve is more flat. It is not very good. It's not great. It's not terrible, but it's because there's so much variance. There's so many variations in making my ice cream that if I look at the curve, it's pretty low. How do I improve the process? Well, I increase 6 sigma. I use my 6 sigma methodology, or I use PDCA, and I find a way to improve how we make ice cream. So some of these ice cream containers are being filled. They're not great. I want them to be a little bit better. I want them to either have less or more depending on the observation of the ice cream. So I go a little bit further. I implement an appraisal cost. So if somebody's observing ice cream as it's going through, and then they can manually add some or take some away or stop it early. So now my process is better. Notice in the red graph here, it's gotten taller and it's not as wide. So between the lower and upper specifications, I'm better off. As a matter of fact, if you look at the graph of the lower and upper specifications, it's virtually 0, which is great. What's happened is since my process has gotten better, the 66% of observations on either side of the mean are now much smaller, because I'm actually hitting 2.6 liters or 2.4 liters, much closer to that 2.5, almost consistently. And because the graph has gotten better, it's gotten taller, it's not as wide, and the standard deviation of 1 standard deviation is much smaller. So if I were to measure my standard deviation from one side to a specification, let's say the lower specification in this example, I now have more standard deviations because the standard deviation is much smaller. The process is much better. So in this case, it's 4 standard deviations, or 4 sigma, from the mean to the lower specification. And again, because it's a normal curve and balanced, it's symmetric, it would also be 4 standard deviations from the mean to the upper specification too. So because the process has gotten much better, we've improved it, it's gotten taller, which means the amount of observations we see are closer along the mean. And so our process is great. This is 4 standard deviations. Now, if I go really far out and I really want to make almost every single tub of ice cream fill to 2.5 liters, have very little variation. Notice here in this blue graph, again, that's much taller because we're always seeing almost every time 2.5 liters. Process has gotten much better. The amount of observations at the specifications, so 3 liters or 2.0 liters, is almost 0. And really, the variation we're seeing is almost around the mean. So we're looking at a smaller sigma. Most of my observations are 2.5 or around 2.5. Again, the graph is taller because the process has gotten better. The standard deviation has gotten smaller. And now there's more standard deviations to measure from the mean to the lower spec. So right there, you see that there's more standard deviations between the mean and the lower spec, which means I'm now at a 6 sigma process. My process has gotten so good, there's almost no variation. And that's fantastic. So if I take all 3 of these and put them together, you can see as we go from 2 standard deviations up to 6 standard deviations, it's much easier. It's much better as far as the process is concerned. We're consistently hitting 2.5 liters on my ice cream, or 13 ounces in my bag of chips, or 6 inches on my phone. So I'm doing much better in my process. Now here's the great thing. If you have a 6 sigma process, you are nailing it. As a matter of fact, we're going to talk about this in just a moment, right here. As you look at the Six Sigma level from 2 standard deviations to 6 standard deviations, look at the number of defects per 1 million items made. 2 standard deviations, again, the curve had some variation, and around the upper and lower specifications, there was some amount of product defect. There were some things, some containers of ice cream we were throwing out. Well, about a third of a million ice cream containers will be defective. And so you throw it out, and that's a waste in cost, et cetera, a waste in process. 2 standard deviations is okay. It's better than not having any, better than having one, but it's still pretty weak. Now, notice as we go up and the number gets higher in our standard deviations, we have fewer defects per million. So 4 standard deviations, the process is much better. That was our picture in the middle with the red curve. Only 6,000 are being thrown out because our process is tighter. It's better. We're seeing around the curve, around the mean more often than we had before. So 6,000 are being defective, but out of a million, that's pretty good. And then again, from Six Sigma, only 3.4 are being discarded. Again, it's really hard to hit 0, but let's look how small that is, 4 compared to a million that are being made. That's awesome. The problem with Six Sigma is it's really hard to get there. You have to throw people, resources, money, etc., to make a process that tight. And again, practically speaking, let's see Six Sigma from a practical perspective. So on the left of this chart is the classical view of quality, 99.9% good at 3 standard deviations, 3 sigma. And then on the left side is Six Sigma view of quality, 6 standard deviations, 6 sigma. Now on the on the right side, you're looking at 99.99966% satisfaction. So which means 99.99966% of products are going to be good. You don't have to throw them away. That's really hard to get to. Now, if you look at the left side, 99.9% good. Wasn't that good enough? I mean, 99.9% is pretty wonderful, but 99.99966% is even better. But to get from the left to the right, you have to put a lot of money into it, a lot of time and training and thought. And how do I make this process so good that it's only got 3 defects or 4 defects per million? So some examples on either side. On the left, 20,000 lost articles per mail per hour. On the right, 7 lost articles of mail per hour. On the left, unsafe drinking water for almost 15 minutes each day. Or on the right, 1 minute of unsafe drinking water every 7 months. On the left, 5,000 incorrect surgical operations per week, which is a lot. On the right, 1.7 incorrect surgical operations per week, which should still scare you. Because if you're one of those 1.7, that's not good, right? But mistakes happen. But look how much less it is. So 5,000 versus 1.7. So when you have a process that is Six Sigma, it's a lot better, a lot easier, and probably a lot more relieving if you're the patient. On the left side, 2 short or long landings at most major airports every day versus 1 short or long landing at most major airports every 5 years. So just the number of flights that take place in a year, and then seeing how many different or how often you have those failures. On the left, 200,000 wrong drug prescriptions each year. On the right, 68 wrong drug prescriptions each year, which should still scare you if you are a person who is on medication, right? So is Six Sigma good enough is the question. But the example that I use on the last one is no electricity for almost 7 hours each month. On the right, 1 hour without electricity every 34 years. I mean, obviously there's a big difference between those two. Here's the one that I would say. Let's say you have a pacemaker. You know, are you comfortable with Six Sigma? And that there's a 1 in 1,000 chance that it's going to fail versus a 1 in 500 chance it's going to fail, or 1 in 10,000, I think it is. Regardless, one failure is bad. If you have a pacemaker and your heart needs to beat, that still can be fatal. And so again, it's hard to get to Six Sigma, but is it worth the effort to get there? And in some cases, the answer is yes. In some cases, the answer is no. Regardless, if you have a quality mindset, you're always shooting for that Six Sigma. And a formalized process of Six Sigma is looking at a process. How do we improve the flow, flow time? How do we improve the capacity? How do we improve the process so people don't get hurt? So that there are no failure defects, there's no external failure costs. That's the goal of Six Sigma. Okay, so let me close out of this and then get back to the other one. Well, here we go. Right. So we talked about histograms now. You kind of have a basic understanding of Six Sigma. We're going to do a problem and it'll be up next week. It'll show you kind of how Six Sigma works, not just pictorially as we saw on the screen, but also a little bit more into the details of what it looks like, a little bit of math. I don't want to throw a lot of math at people right now. I just want you to understand the concept of Six Sigma. It's really the penultimate of where we're looking for when we're trying to understand how to improve my process and make it nigh perfect every time and continuously have that consistency. Now you can see the value of the inconsistency when it comes to a service product, right? When it comes to a service that somebody is getting, I want to have consistency from that haircut every time from the same person. Well, if the process is Six Sigma, it's probably so routine, so rote, written down, so that people can see it and understand that every time I get a haircut from the same person, I'll still have the same type of haircut. I'll still be happy with it. But it's hard to get there with people because people have bad days. They have things on their minds. Sometimes they're having they're rushed. They're trying to get things done. It's just there's a variability. But Six Sigma is trying to take the variability out of the process. Okay. So here we're going to do another diagram, another picture, another tool that we have. This is called the cause and effect diagram. It's also called the fishbone diagram because it looks like a fishbone. And there's something called the 4Ms. And I've done this in person in a manufacturing environment where we need to improve the quality or we need to improve the time with our process, and I don't know where to go. And so we take 4Ms: manpower, machines, methods, and materials. So manpower is labor, machines is the capital equipment we use to make stuff, methods are the processes we have in place, materials are the inputs. So I look at all four of these and I say, okay, based on how we do something, how we do a process, what can I replace? What can I improve on? So it's more of a brainstorming session. And this might be a bit of an eye chart, but this is kind of what it looks like. So we have the 4Ms. You can see the diagonal lines coming off. Manpower, machines, methods, and materials. And in this case, we have a lack of responsiveness to our customers. That's the biggest complaint that our customers are saying. So how do we do this? Well, we start putting together every time somebody calls my company, what do they go through? From a materials perspective, we're not computerized. We have an awkward, there's a complaint forms. What are some of the complaint forms that we have poor design for our product, or our customer service is poorly designed because we don't get to people drop off the calls. There's several suppliers that we work with. We have variable quality on the products that they buy. And so if we could nail it down to one supplier, it'd be even better and cheaper for us. Excessive red tape, if they're going in to try to do something, to fix something on their own, and make it difficult to do so. From a manpower perspective, we have a lot of people who are traveling. We have field engineers who are out there working on things. We have inadequate tools to our field engineers. We also have no customer focus. We have managers that are doing a lot of things, and some of them are not addressing their main problems. And so there are challenges there. Sometimes we don't follow up. And so what we're doing is we're just kind of brainstorming, hey, what are the main issues with customer service? Why do people feel that way? And if we look at manpower, machines, methods, and materials, we start brainstorming ideas as to what are some roadblocks? What are some bottlenecks? Remember that? What are the bottlenecks to my process? How can I go about improving quality? By looking at the big picture. And then in a group form, we just kind of circle items that are things that this is really a big problem. So for example, you can see under manpower, it says telephone staff at the bottom of that diagonal. And tied to that says not trained. Well, our telephone staff are kind of rude sometimes, or they don't speak English well enough. And so we need to really focus on getting them to speak, because sometimes customers often on recorded calls are saying, what? Well, I'm sorry, what did you say? Beg your pardon? And so if we can train them, that could be a simple way to improve quality. Or if we have insufficient lines, so if our lines get overloaded, our machines, it's our technology. And as they get overloaded, sometimes people get dropped off and then they get mad. I'm going to call again, et cetera. And so insufficient lines, maybe if we had more lines that they could wait and hold on to with our network, that would be better. So a cause and effect diagram is just looking at everything that's possibly on the table. How do we improve this? right? Again, it can get kind of crazy, but it's based on these 4 M's: manpower, machines, methods, and materials. So we could do a cause and effect diagram. We won't actually do one, but we'll just kind of assume, what about Franklin College? Like, what are some things that irritate you about Franklin College? And one that often comes up is the cafeteria. Well, what are problems with the cafeteria? What are some of the manpower issues with cafeteria? Is there not enough people working there? Are there not enough people cleaning it? Are there more people there than they need? Are people standing around doing nothing? Do they have the training? Maybe do they have the training to make food, make good food? I don't know. Maybe it's the materials. Maybe it's the supplies. It's the vendors we get the food from, right? So manpower would be that we don't cook the chicken well enough. Materials is we get poor quality chicken to begin with. Machines, well, maybe it's the ovens that are a problem. Maybe it's the refrigeration that's the problem. Maybe it's the counters that you interact at. Maybe it's hard to see or hard to hear. Maybe it's from a, I guess technically a machine would be the plexiglass at the tables. Can you talk to your friends easily enough? Is it hard to hear? So because of coronavirus. Methods, what do we have? You have to have a pay when you get in. Well, can't you see what's available first and then pay on your way out? That's what a lot of cafeterias do. Why do you pay on your way in? And so does that process, that method, make the most sense? And so again, we start brainstorming. Well, how would we go about changing that? Or what are some continuous problems that I see over and over again at the cafeteria? And so we kind of measure that. So that's what a cause and effect diagram is. It's a brainstorming session to improve quality and try to find those bottlenecks. Another one I want to go over is Pareto analysis. A Pareto analysis is the 80-20 rule. 80% of problems are caused from 20% of causes. Now you'll see this in other contexts too. But 80% of problems are caused from 20% of causes. In other words, if you can gather data on your common issues and sort them from greatest to least, focus on the top 2. So if I have 10 problems, just focus on the top 2. Because if you focus on the top 2, that will eliminate most of your problems. And then those that are less offenders aren't going to be as big of an issue. So for example, what are the biggest problems in going to a movie theater? Well, going to a movie theater, gosh, remember those days when you could go to a movie theater? So when you go to the movie theater, what are the biggest problems? Well, it's too expensive. That's one. Or it's too cold. Man, it's just always cold every time I go to the movie theater. Or it's not the cleanest, right? Or maybe the seats just aren't comfortable. After about an hour and a half, I find myself squirming around in the seats. And so it's a challenge there. Or people are talking. They're on their phones. I can see the light from their phones, or people are talking. And so I take the 10 most prevalent issues in going to the movie theater, and then I just focus on the top 2. The temperature, it's too cold, and the price of the movie, or the price of concessions. So then you focus on those 2, because you can eliminate a lot of the complaints just by doing those 2. So do you have a bundle deal, or if you buy it online, you can have a cheaper price for the tickets? Or maybe if you're going to buy food, popcorn and soda and nachos, then maybe you get a discount on your ticket. You get 40% off your ticket, although guaranteeing you're actually going to go ahead and buy the product, right? So I'm going to continue to get that product. So anyway, all these different things are here for that. So Pareto analysis is the 80-20 rule, okay? So 80% of the problems come from 20% of the causes. And if we focus on the first 2, that'll help us eliminate some of those. So I'm at past time. I'm going to stop it here. I'm going to stop the recording. But we've done a lot.